All right, just need to do a technology check. Campbell River, can you see me? And can you, well, obviously you can hear me. Probably can't see the content yet. Should be able to see the content now in Campbell River? Yep. All right, how about College of the Rockies? Can you see the content? Yep, and obviously you can hear my voice. All right, so when we finished last time, we calculated internal stresses on two-dimensional and three-dimensional problems. And we're just moving on to calculating or drawing the shear and moment equations and diagrams so that we can figure out basically where the maximum shear and bending moments are going to be on a beam for design purposes. So the way we're going to do that is we're going to calculate the shear and moment as a function of x. And it's going to be calculated by using the method of sections, but we're going to cut our section at an arbitrary distance x from the end. We have to do each section of the beam separately. Every time there's a point load, we're going to have to draw a new section and do a new calculation based on that range of x values. The graphs will be discontinuous wherever the loading changes. So we'll see that, and we'll plot the diagrams directly under the beam to give us an idea of where on the beam the forces are going to exist. Oh, you lost the content in Campbell River? Okay, just a second, I'll just try and cycle through. Oh, no, I've lost Campbell River totally. Is he back?
Yeah, I can't see you now.
You can't see me, but you can see the content?
Yeah.
Okay. Content's more important anyway. As long as you can hear my voice and see the content, I think that's the most important. So here's a simply supported beam. So it's got a pin joint on this end, a roller on this end. We want to draw the shear and moment diagrams. So what do you think we should do first? We're going to have to find the reaction forces so that we can, so when we take a section, we've got at least some kind of a force to work from. So we would find the reactions at A, which are going to be a y component force and an x component force, but by method of staring, we can probably guess that that x component is going to be 0. And at B with the roller, we can only have a y component. All right. Anything else on our free body diagram? Nope, that's it. Our three components of reaction. They would make it fully constrained or properly constrained. What next? Equations of equilibrium. So our equations would be sum of the forces in the x equals 0, which we've basically already used. We have the sum of the forces in the y equals 0, and we have to come up with a moment equation for our third one. Where would you like to take the moments about? Yeah, either A or B would be an equally good choice. So if we take our moments about A, is this 9 kilonewtons positive or negative moment? It's going to be a negative moment. So that would be negative 4 meters, 9 kilonewtons. And then By would be a positive moment, so plus 6 meters By. Yeah, so it's going to be 2/3 of the 9 kilonewtons, or 6 kilonewtons. And then our other equation of equilibrium would be net force in the y direction equals 0, AY minus 9 kilonewtons plus BY, which is 6 kilonewtons, therefore AY equals 3 kilonewtons. All right, what are we going to do next? We're going to cut the beam in a somewhat arbitrary point X. We're going to make sure it's between the support at A and this point load. So I'm going to label this point here C. So we're going to cut an arbitrary section between A and C. So cut a section, an arbitrary distance x, or between A and C. All right, so we're going to cut our section right there. Okay, so this distance here is going to be x. At the section cut, we would have potentially a normal force, except we should be able to tell again by staring. The normal force is going to be 0. We would have a shear force. What direction should I draw the shear force in? Down. Positive shear force is down. So we'll assume it's positive, and I'm actually pretty sure that it is going to be positive. Oops. So that's v as a function of x. And we would also have a moment reaction at that section cut. If it's positive, what direction is it going to be in? Counterclockwise, because it's a left section, and that would produce a concave upper surface. So that would be m as a function of x. Now what? Equations of equilibrium. So if we start with net force y equals 0, I've only got two forces. I've got AY, which is up, and I've got, V, the shear force, as a function of x, that's down. So that means Vx equals AY equals 3 kilonewtons. Anywhere between A and C, the shear force is going to be the same. It'll be a constant 3 kilonewtons. All right, what about the bending moment? To find the bending moment, we're going to have to find the moment about a point. What point should we use? I could either use A or this arbitrary point here, x. It doesn't matter. So since A is fixed, we'll do the moment about A. What's going to produce a positive moment about A? Right, the bending moment is a function of x. And what's going to produce a negative moment? Right, the shear force times x is going to cause a clockwise rotation, so we'd have minus x times 3 kilonewtons. So m of x equals 3 kilonewtons times x. So this is a constant and this is a straight line function. All right, so that's going to work for everywhere between A and C, but at C the loading changes. So we're going to have to do another section, an arbitrary distance x. Again, we're going to measure from the left edge, A, but x is going to be between 4 and 2. So the section is going to be between C and B. I could also do a right section, but if I'm doing a right section, it's going to be hard for me to show where my x is, because my x is measured from the left edge. I could do it. I think it's going to be less confusing, at least for the first one, just to draw another left section. You would get the same results. All right. What do we need to add to our free body diagram of the section? Same thing as before. And again, if we're assuming that the shear force is positive, it would be down. If we're assuming that the bending moment is positive, it would be counterclockwise. And we're going to find those the same way we did before. So to find the shear force, we're going to look at the sum of the forces in the y direction equals 0. So I've got AY, which is up, so that's the 3 kilonewtons. I've got the 9 kilonewtons that's down. And I've got VX, which is down. What is my shear force as a function of x? Negative 6 kilonewtons. So it's a constant valued function again. To find the moment, bending moment, take the moments about A. So the moments about A is going to give me it's going to give me mx. It's the only positive moment I've got. And I've got minus 9 kilonewtons times 4 meters. 9 times 4, 36. And then we're going to have minus x times Vx. Since Vx is positive, that actually makes that plus 6 kilonewtons times x. Okay, so if I solve for the bending moment as a function of x, what do I get? Right, we get 36 kilonewton meters minus 6 kilonewtons times x. So that's a straight line function again. Okay, so we're going to take those 4 functions, right, the 2 shear functions and the 2 moment functions, and we're going to draw them on graphs that are underneath the beam. So the first one's going to be our shear diagram. So we're going to draw the shear diagram in blue. So between A and C, what does the shear diagram look like? Straight line at what value? 3. And then at C we have a discontinuity, as it jumps from 3 to minus 6. Okay, and this isn't a very exciting graph. I'll make it a little bit more exciting. I'm going to kind of shade in below the graph. Normally that's what's done on the shear and moment diagram, and we'll learn why that is probably later today, if you can't guess. So we'd shade in this area, and then we would shade in this area. Okay. What about our moment diagram? What's it going to look like? Oh, I should use a different color. Let's use something that shows up. Let's use purple. So what does the moment diagram look like? All right, so that's right. So between A and C, it's a slope of 3 going up. So it goes from 0 at x equals 0 to 12 at x equals 4. We go to from 0 to 12 kilonewton meters. Purple color. And then what happens between C and B? Well, it doesn't actually start at 36, because it starts at x equals 4. And at x equals 4, this is going to be 36 minus 6 times 4, which would be 12, right? So it's actually going to start at the same point where the other one finishes, and then it's going to continue with a slope of negative 6. And continuing with the slope of negative 6 for another 2 meters, it finishes up at 0. We'll shade that one in as well. Okay, so that's our shear and moment diagrams for that simply supported beam. That was not all that exciting, but it gives us a start. So look at a little bit more interesting loading here. The next problem is a cantilevered beam. So the cantilevered beam is supported only at one end, and the reaction at that end would be potentially 2 force components, so X and Y forces, and also a couple moment that's preventing it from pivoting about to point B. And in this problem, we're told that the length of the beam is 18 feet, and the beam itself has been designed to withstand a shear force of up to 800 pounds and a bending moment of up to 1,200 foot-pounds. So we want to determine the largest intensity W of the distributed loading that it will support. So, and this is not a uniform distributed loading, this is a triangular distributed loading. What should we do first?
Change the into a single force.
Okay, to what end? And how do I know what Vmax is? Oh, sorry, I know what Vmax is, but that's not going to tell me necessarily what this equivalent force is. Normally in a problem like this, the first thing we would do is we'd find the reaction forces. Except if it's a cantilevered beam, because as long as I take the left section, there aren't any reaction forces. So I can do a free body diagram of the left section without figuring out, sorry, I'm pointing at my screen without using the pen. I can figure out the forces on a left section without figuring out the reactions at B. And in fact, if I find the reactions at B, I'm not going to use them to find those shear and bending moments on the left section anyway, because they're not acting on the left section. So I'm not going to do that this time. And in general, on a cantilevered beam, you don't have to find them. By the time you do the shear and moment diagrams, the values we have at the end are going to be the reaction forces at that support end. So our first step this time is actually just to take the section, an arbitrary distance x from A. And because the loading doesn't change along the beam, it's going to be one continuous function. So my section is going to look like that. How high is this? If this is W out here, what's this height going to be? Sorry? Nope. It's a similar triangle. So if this is W and L, then this is going to be WX over L. All right. So I've got this loading. What else do I need to put onto this free body diagram? Shear force and bending moment. So our shear force, we're going to draw down, even though I'm pretty sure it's going to be up since there's no upward forces to balance it. So that would be V as a function of X. And then we'll draw in our positive bending moment. All right, now what do you want to do? I'm not quite ready to write my equations of equilibrium because I have this distributed force that I'm going to have to simplify first. So I want to replace this distributed force, or the distributed loading, with a single force. All right, where's the point force going to act? Right, so it's going to act through the centroid, which is a third of the distance from any of the sides. So that's going to be at 2/3 of x, because we've got a flat side here at the distance x. So that's where we're going to put our equivalent force. Just call that F. And that distance is going to be 2/3 of x. What's the magnitude of that force going to be? Or how am I going to find the magnitude of that force? The area of the triangle. So if we could integrate it, or we could just calculate the area of the triangle. So it'd be 1/2 base times height. So 1/2, the base is x, and the height is WX over L. WX squared over 2L. All right, now I can do my equations of equilibrium. equations of equilibrium are net force y equals 0. What have we got going in the y direction? Right, so I've got minus wx squared over 2L, and I've got minus v, assuming v was a positive shear. Obviously v is not going to be positive shear. So if we solve this, v equals negative wx squared over 2L. Okay, and what about our bending moment? Oh, that's v of x. Well, we're going to have to use a moment equation. Where would you like to take the moments about? A would work. So moments about A equals 0. So I've got the moment, sorry, start with the positive moment. I have the couple moment, which is the bending moment, m of x. And then I have the moment that's produced by the downward force here. And then I'm going to have the moment that's produced by the upward shear force here. So since the shear force is actually upward, that's going to be a positive moment, x times w x squared over 2L. And then I'm going to have a negative moment for that one, so minus 2/3 x times also wx squared over 2L. So if we solve that for m of x, so negative x cubed, or wx cubed, over 6L, right? So the 1/3 of the 1/2. All right, and that's going to be the same for the whole length of the beam. Where's the maximum bending moment going to occur? Where is this function going to be maximum? When x is L. Yeah. Where's the shear force going to be maximum? When x is L as well. So both shear and bending moment will be max at B when x equals L. All right, so we'll calculate those values after we draw the shear and moment diagrams. So let's start with the shear diagram. What's the shape of the shear diagram going to be? It's going to be parabolic. So it's going to start at 0 and with a slope of 0. And it's negative, so it's going to open downward like this. And it's going to reach a maximum value here. And that maximum value is going to be Wx squared over 2L when x equals L. WL over 2. Negative WL over 2. Okay, and then we'll shade in the shear diagram. And we know that WL over 2 has to be less than or equal to 800 pounds. What's the bending moment diagram going to look like? It's a cubic. It's going to look similar to the parabolic curve, but a little bit sharper. Okay, and it's going to reach a maximum value here again when x is equal to L. So we would substitute in x equals L, that would be WL cubed over 6L, which would be WL squared over 6. And it's negative. WL squared over 6. And that has to be less than or equal to 1,200 foot-pounds. And then we can shade in the moment diagram. All right. How are we going to figure out what our maximum loading is? Right, so if we solve both of these for W when L is 18 feet, we have to choose the smaller of the two. So if L equals 18 feet and V max is equal to WL over 2 would be 9W. 9W is less than or equal to 800 pounds. So that gives me W is less than or equal to 88.9 pounds. And M max if L equals 18 feet, that's going to be W times 18 squared. So it'd be 81 times 4, 244? 324? That's what I said. So 324 divided by 6. 54. So M max is equal to 54 W, which has to be less than or equal to 1200. So that tells us W is less than or equal to 22.2, and that's pounds per foot. Which one do we choose? I always choose the lower one. So as I mentioned before, these values of shear and moment on the right side are going to have to be the components of reaction at B. Right, there's going to be an upwards force at B that's going to be equal to WL over 2. And there's going to be a, let me get this right. There's going to be a clockwise support moment at B that's going to be equal to WL squared over 6. All right, so you may have noticed in both of the cases that we've done here, there's a similar relationship between the shear diagram and the moment diagram. In the first case, we went from a constant function to a straight line function, or two constant functions to two straight line functions. And in the second case, which was a little more complicated, the shear diagram was a parabolic function, or a quadratic function, and then the bending moment was a cubic function. Based on that, can you make a guess at what the relationship might be between the shear diagram is the derivative of the moment, or the shear at any point is the derivative of the moment? That's exactly right. So a beam may be subjected to a number of concentrated loads and one or more distributed loads. So here's a problem that you wouldn't want to have to solve. We've got an ugly distributed load. I got 2 point loads on here, 2 different couple moments that are applied at different parts of the beam. And then we would want to draw the shear and moment diagrams. It's actually not that difficult. For the purpose of this discussion, we will consider upward loads to be positive. So this distributed load here is positive. That's not normally how loads occur on beams. Normally the loading is downward, so we would call that a negative load. Distributed load can be expressed as a function of x, so W as a function of x. So if it's a straight line, a uniform distributed load, then W of x would be a constant. If it's a triangular load, then Wx would be a linear function. And if it's something like this, then it would be a more complex function. For any point on the shear diagram, the slope is going to be given as dV dx equals the distributed magnitude of the distributed loading. That's why on the first example there was no distributed load, so the shear diagram had a slope of 0 everywhere, except where it was discontinuous. So it had an undefined slope. But anywhere between the point loads, the slope was 0. In our second example, we had a distributed load here that's a straight line function. So the slope of the shear diagram here is equal to the value of this distributed load function. So we're starting with a slope of 0, and it increases to a slope of W. Right? What's the derivative of Wx over 2? Oh, yeah, that would be W over 2. Oh, but this is Wx squared over 2L. So the derivative of Wx squared over 2L would be Wx, which is the other function. Or WL over... No, Wx over L. Wx over L, which was this function. This is W as a function of x equals Wx over L. All right. So the slope of V is W. By integrating, we can find the shear is equal to the integral of Wx dx. So that's kind of like the same relationship as what's expressed here. If V is the integral of W, then W is going to be the derivative of V. Note that at concentrated loads or point loads, the shear diagram is discontinuous. That's what we saw in the first example. We had a jump at the shear, at the point, a jump in the shear force at the point loads. And it jumps by the magnitude and in the direction of the concentrated load. Let's go back up and check that as well. So there's actually a point load at A, which is upwards. That's the support reaction. That was 3 kilonewtons. So right away, we jump up to 3 kilonewtons. Goes with a slope of 0 because there's no distributed load until we reach C. C is a concentrated load of 9 kilonewtons down, which means we jump down 9 kilonewtons. So from 3 kilonewtons down to -6. No distributed load, so it continues straight across at -6 until we get to B. And then at B, there's a concentrated force of 6 kilonewtons upwards, the reaction at B, which brings it back to 0. They should all begin and end on 0. In this one, there are no point sources, so that's why the graph was continuous. It's a single continuous function because there's no point forces. Well, sorry, there is a point force. There's a point force, sorry for skipping around here. There's a point force at B. And there's a point force at B because we have to go back to 0 here. So this point force at B brings this graph back to 0. So it's going to be a positive force because it's an upward force on B that's going to be equal to the area under this graph, which is going to be equal to the value of V here. Right? V is the integral of W. All right. Moving on to the moment diagram. The slope of the moment diagram is going to be the value of the shear diagram. By the same argument, the change in the moment over any distance is going to be the integral of the shear force as a function of x. At the maximum moment, the shear will be 0. Why does the maximum moment have to have a shear of 0? Put a thing in here, or undefined. That's right. Because the shear diagram is the derivative of the moment, it's going to be 0 where it stops increasing and starts decreasing, or where it stops decreasing and starts. It's going to be a min or a max, local min or max. And then I put in here or undefined because in the case of our first diagram, skip back up here, I can't really say that the shear is equal to 0 here, but it crosses 0 here. It goes from a positive value to a negative value, and that's where our maximum moment is going to be. It's actually going to be undefined at this point because it's a vertical line. Okay, and if we have a couple moment acting anywhere on the beam, then that's going to cause a discontinuity in the moment diagram, and it's going to jump by an equal amount to the couple, a clockwise couple being positive. So note that if Wx is a polynomial of degree n, so in our second example that would have been degree 1 because it was a straight line function, then v of x will be a polynomial of degree n plus 1, i.e. it was a quadratic function, and m as a function of x will be a polynomial of degree n plus 2, i.e. it was a cubic function.
Where in the graph are the couple
right where the couple moment is applied.
Because at the couple moments were applied.
Okay, so that's a good question, because earlier when we were doing the analysis, we said it didn't matter where the couple moment is applied, and that's true as far as finding the reaction forces. As far as finding the internal forces, it matters where you put the wrench that's going to be applying that couple moment. So we would put that discontinuity at the place where we are applying that torque or couple moment. All right. So in this case, we're going to draw the shear and moment diagrams for this double overhang beam. And we're going to draw these moments using what we've just calculated, or what we've just discussed, sorry. But we're not actually going to have to use any calculus. We're just going to use our knowledge of calculus to draw the diagrams. So what's the first thing that we should find? The reaction forces at A and B. Okay. How long is that going to take us? No, less. What's the reaction force at A? Nope. Nope. Okay, so by the symmetry of this problem, we can tell that AY and BY are going to be the same. So we could go through the process of writing the moment and everything, but if you can see the problem symmetric, save yourself a little bit of time. And just put in the reasoning. By symmetry, AY equals BY. Oh, and what about AX? AX is going to be equal to 0. Okay, so we know everything we need to here to draw the shear and moment diagrams. What's the shear diagram going to look like? Oh, yeah, sorry. I should fix that. Oops. Equals 10 kilonewtons. Oops. Shit. Oops. Ah, crap. Go back. I lost one of my lines. There we go. Okay. What's the shear diagram going to look like? So we've got a point loading right at the end here of 5 kilonewtons, which is down. So that's going to cause an immediate jump in the shear diagram from 0 down to negative 5 kilonewtons. And then at point A, I have the support reaction, which is 10 kilonewtons up. So what's the shear diagram going to do? It's going to jump 10 up, so from minus 5 up to plus 5. And then between A and the center here, it's going to stay at plus 5. All right, and then what happens in the center? It goes down by 10 kilonewtons. So it goes down to, back to negative 5. Stays at negative 5 over to B. At B there's a support reaction of 10 kilonewtons. Goes back up to plus 5. Stays at plus 5 over to the right edge of the beam, and then there's a point load of 5 kilonewtons. Of negative 5 kilonewtons because it's downwards. Goes back to 0. There's my shear diagram. What's the moment diagram going to look like? It's going to start at 0. Hang on a second, let me just... I'll go to purple again, M of X. So it's going to start at 0. Slope of negative 5 for 2 meters. Oops. Okay, where are we at now? Okay, so it's going to be negative 10 kilonewton meters. And then it goes to a slope of plus 5 for another 2 meters. So by symmetry, that would bring me back to 0 again. And then it's going to do the same thing again. And then back up. Whoops. Again. Oops. And then we'll shade that in. Okay, so there's my shear and moment diagrams based on the relationship of the integral or the derivative, where we didn't actually have to do any calculus. We just looked at the slopes. All right, the next one's going to be a little bit more challenging, but we can still do it. So this problem says draw the shear and moment diagrams for the shaft and support at A is a thrust bearing and at B is a journal bearing. So if A is a thrust bearing, then what would the components of reaction be at A?
X and Y.
We could have X and Y. My method of staring, I think the X is probably going to be 0, but we'll draw it in so that it's fully constrained. And B is a journal bearing, so it's only going to support a reaction in the Y direction. Well, it would also have a reaction in the Z direction if we were looking at a three-dimensional problem. All right, what do we need to do first? Right, we're going to need to find these reaction forces, so I know where to start on my shear diagram. And to find these reaction forces, I think the first thing we're going to want to do is replace this distributed load by an equivalent point load, or an equivalent concentrated load. So let's put that in as step 1, find reaction. Forces, and part A is going to be replace distributed load with concentrated load. F. Where are we going to draw F? Right, it's a rectangular shape here, so we would draw it halfway between at 0.4 meters. Okay, and how big is F going to be? Right. So it's going to be the area of that rectangle, so that's going to be 2 kilonewtons per meter times 0.8 meters equals 1.6 kilonewtons. All right, so we've done part A, and we would move on to the equations of equilibrium. So our equations of equilibrium are going to be some forces in the y direction and some moments about some point. What point should we use for our moments? It doesn't really matter. I could use A or B. A's a little bit easier just because I've got all the measurements are directly from A, but it doesn't really matter. So if we do moments about A, there's only one positive moment about A, and that's going to be from the reaction force at B, which is 1 meter away. dy. And then there's going to be 2 negative moments, one from the distributed load at 0.4 meters. And one from the concentrated load at 0.8 meters. Concentrated Concentrated load is 4 kilonewtons. All right. What do we get for By? Point 0.8 times 4 is going to be 3.2, and 0.4 times 1.6 would be 0.64, so 3.84 would be. By equals 3.84 kilonewtons. Then we can do the net force in the y direction to find what AY is. AY plus 3.84 minus 1.6 minus 4 kilonewtons. .76 kilonewtons. All right. So we could do the section cuts and figure out the shear and moment as a function of x, like we did in the first section, or we can just use what we know about the relationship between the distributed loading and the shear force and the moment diagrams to produce them. I'd say using calculus, except we're not actually using any calculus. We're using the concepts of calculus, of one being a slope of the other, one of the functions being a slope of the other. We need a new page. A copy of the beam. I should have taken a picture of this before I marked it all up. Okay, so our shear diagram is going to start at what value?
Zero.
Okay, it starts at 0 and then immediately jumps in which direction? So the shear diagram starts at 0 because it always starts at 0, but then there's a concentrated load at A due to the reaction force. So that means it's going to jump up by AY, which was 1.76 kilonewtons. Let me just move that up a little bit. Okay, or 1.76 kilonewtons. Now what happens between A and 0.8 meters? It goes down linearly because I have this distributed load here, which is downwards at 2 kilonewtons per meter. So that means the slope of this is going to be -2 for 0.8 meters. How far is it going to go down? 1.6. So it starts here at 1.76 and goes down to 0.16. Because this has a slope of -2 kilonewtons per meter. All right, what happens at 0.8 meters? It takes a jump of 4 from the concentrated load. So if it goes down by 4 from 0.16, what value does it go to? 3.84, -3.84. Okay, and then what happens between here and B? Whole lot of nothing. So it goes straight across, and then what happens at B? There's the point loading here, which is going to bring it back up to 3.84. If we don't start and end at 0, we've made a mistake somewhere. So this is -3.84 kilonewtons. And then we'll shade in this area. You can see why we're shading in the areas now, because when we go to the moment diagram, I'm just integrating this function. So that's why I'm shading it in, because we're going to calculate the area under the graph. Well, we're not really calculating the area under the graph, we're just using this to calculate the slope of our other function. All right. If that's our shear diagram, what's the moment diagram going to look like? Where does the moment diagram start? 0. There's no couple moments applied at A, because it's not that kind of support, right? It just has x and y components, no moment. So that means it's going to start at 0. What's the slope going to be? Positive. Well, it's going to start with a slope of 1.76, but the slope's going to be decreasing to 0.16. So it's going to be almost, well, a lot closer to horizontal when it gets to this point. So we would draw that something like that. Okay, so this starts at 0. How am I going to find this value? What's the relationship between the moment and the shear? And this is the slope of this graph, but the values on this graph are the area under this graph. So I could integrate it, but it's a pretty simple looking function. I don't think I need to use an integral to calculate the area. Right? It's just a trapezoid. So I take the average of these two heights, 1.76 plus 0.16 divided by 2, and multiplied by this width, which is 0.1 or 0.8 meters. 0.768. So this value here .768, and that's going to be kilonewton meters. All right, what happens here to the moment diagram? Right. It's continuous here because there is no couple moment applied. It's continuous, but its derivative isn't continuous, which means the slope just makes a jump to a straight line with slope equals negative 3.84 kilonewtons. And if I travel that slope for 0.2 meters, that should bring me back down to 0. If it doesn't, we've made a mistake. So does it bring us back to 0? Yeah. All right. And then I'm going to shade that one in. Okay. You can probably guess by the fact that I'm shading in the moment diagram that there's another one. Well, actually, there's another two. The other two are not actually part of this course. But from the moment diagram, we can get an angular from the moment diagram and some properties of the shape and of the material. So the modulus of elasticity of the material and the moment of inertia of the cross-sectional area of the shape, we would get a angular deflection from the next integration, and then we would integrate it another time to get the actual distance of the displacement. So we're not going to go through those in this class, but that's going to tie together the next section that we're going to do on centroids and moments of inertia. They're useful with these shear and moment diagrams to produce a deflection diagram.
Dennis,
Yep.
wondering where the lecture videos are available?
I haven't posted the lecture videos because we haven't had to. Would you like me to have them posted?
Sure.
Sure. Okay. I'll see if we can put them up on a streaming server, and then I'll just send you the links. Or I'll send Jim the links, and he'll put them on your Moodle page.
Yeah, if you could send it to like Jim and I'll just ask him for it.
Yep. Sure.
That'd be great.
Okay.
Oh, we're having a midterm on Monday?
Okay. So you'd like to have the notes posted or the lectures posted before then? Okay. I'll see what I can do. All right. And we're a pretty good place to stop here. So we'll continue on this material on Tuesday, and I think we'll probably have time. There's another section that I've put in the notes that isn't covered in your textbook, and it's another way of doing these complex loading problems with a method called superposition. So if we can stay ahead of schedule, then I'll go through those as well, because that'll gives you another tool in your toolbox.
Why does the bending moment cause a concave or convex bend in
In V?
the V?
I'm not sure if I understand your question totally. Like if I have a simply supported V,
Yeah.
and I put a load in the center, you can see it's going to go. It's
Yeah,
going to go
like that.
concave.
Okay.
So that means we would have a positive bending moment in our
Yeah.
calculations. That's what we saw where it went up. for the maximum value and then
Yeah.
down.
Yeah, okay. I
So
was
if it's
just,
cantilevered beam, then it's going to cause it to go more concave on the bottom, or convex on the top.
yeah,
That's why when we look at cantilevered beam, we had a negative bending moment everywhere.
Yeah.
So it started at 0 at the free end, and then it increased the maximum negative value here.
yeah. Okay. I was just trying to figure out the conventions as to why the left was positive and the right, or the left was counterclockwise and the right was
Right.
clockwise.
It's arbitrary, but it's so that when we put the two halves together, they're opposites because they're reactions to each other.
And they
The
cancel.
force on the left section is the reaction force to the right section.
Yeah. Alright.